Welcome back to the deep dive. Just look around you, your inbox, maybe, or that pile of research papers you keep meaning to get to, or just endless scroll online.
Hmm.
We all feel swamped by data sometimes, right? It's a lot. Now, try to imagine you're an AI, one of those huge, large language models. You've basically consumed, I don't know, everything. Every book, every article, every website imaginable. But it's all just this massive, tangled dot web, completely unstructured, kind of chaotic. It's like a library where all the books are just dumped on the floor. No order, no catalog. How could you possibly find anything useful or even understand what you're looking at? So our mission today, we're going to take a deep dive into some really critical work that's trying to bring order to that chaos, to help AI not just store data, but actually, understand it. And we're drawing heavily from a lecture note called Tree Maker Ontology Modeling for Hierarchical Structure Knowledge, INDE. It's by Jae Choi, who's an associate professor at George Washington University and also principal investigator of the CAFA initiative. Really fascinating stuff.
Absolutely. And this isn't just about neatness or tidying up. It's fundamental. If we want AI to be genuinely intelligent, reliable, capable of complex thought, it needs organized knowledge. Raw data on its own, it's just not enough. It needs context. It needs relationships defined. It needs to understand what concepts mean. And that's where this idea of an ontology model comes in. Think of it as like the blueprint for knowledge in a specific area. It formally lays out the concepts, sure, but also their properties and, really crucially, the relationships between those concepts.
Okay, so we're building a better brain for the AI, essentially, a more organized one. But what's the real payoff for us? I mean, what do we actually gain when AI has this structured knowledge?
Oh, the benefits are huge, transformative, really. And they tackle a lot of the frustrations people have with AI right now. First off, it massively reduces ambiguity. When AI has clear definitions and relationships, there's just much less chance of it misunderstanding things or giving those weird off-topic answers. Imagine AI trying to read a legal text without structure. Contract could mean anything. Legal document, muscle thing. An ontology prevents those kinds of, well, embarrassing and potentially costly mistakes. Second, accuracy and relevance get a major boost. Instead of just grabbing random facts from that big, messy pool, the AI uses organized contextual knowledge. The output is just way more precise, useful. And third, maybe the most exciting part and allows for much more complex reasoning, logic. We're moving AI from just recalling facts, like memorizing trivia, to truly understanding context and connections. It's the difference between, say, knowing street names and actually understanding how a city map works. Big difference.
That map analogy really clicks. It's giving the AI a framework, a way to navigate knowledge, not just swim in data. So let's drill down a bit. The lecture notes really highlight one specific type of structure, hierarchical representation. Apparently this is the most common way. And pretty intuitive too, sort of mirrors how we naturally organize things. Now the notes mention other types, mereological, topological, tabular. Sounds complex. But for today, we're focusing on hierarchy. Why is that structure so foundational?
Yeah, hierarchy is everywhere, isn't it? Think about company org charts or biology classifications, kingdom, phylum, class. In ontology modeling, it's basically that same pattern. Concepts arranged in levels, subordination. You have broader general concepts as parents. More specific ones are children nested under them. And the really elegant part is what this structure enables, logical inheritance. If you define something about a parent like all mammals have fur, then it's children, dogs, cats, whatever. They automatically inherit that has fur property. You don't need to state it over and over for every single type of mammal. That efficiency is just critical when you're dealing with potentially vast amounts of knowledge.
Okay, efficiency through inheritance. Makes total sense. Now, the lecture notes break down hierarchical relationships into two main flavors, and this seems really key to the AI's logic. There's the A relationship and the part of relationship. Let's tackle ISA first.
Right. The is-a relationship forms what's called a subsumption hierarchy. This is probably the most common one you'll see. It's the foundation for building formal taxonomies. Categories and subcategories. Simple example of poodle is a dog. Clear type-subtype link. The notes use a good one too. Ford Bronco is a four-wheel drive vehicle, and then a four-wheel drive vehicle is a car. See how it nests. Each level gets more specific. And the reasoning power this unlocks for AI is, well, immense. If the system knows a general fact like cars have wheels, it automatically figures out a Ford Bronco has wheels too, because it is a car. You don't have to feed it millions of separate facts like this specific car has wheels, that specific car has wheels. It just inherits. It allows the AI to make logical deductions from categories, not just memorizing isolated data points.
Okay, so ISA is about classification type. What about the other one you mentioned, the mereological hierarchy? That's the part of relationship.
Exactly. This one's about composition. how things are made up of smaller components. It describes how parts fit together to make a whole. Structural relationships, functional ones too. So the classic example is an engine is part of a car. And you can go deeper. A piston is part of an engine. This is absolutely vital for understanding how systems work or how they break. Think about an AI trying to diagnose a car problem. This part of hierarchy is its map. It lets the AI connect a symptom, say a faulty piston, to the engine's function, and then connect the engine's problem to the whole car's behavior. It understands the dependencies. It's not just knowing a car has an engine, it's knowing how the piston relates to the engine relates to the car. That's deep understanding.
So we have these two powerful ways of structuring relationships. Is Aerofardos part of components? But how do we, actually represent these? How do we visualize them? And critically, how do we make them understandable for an AI?
Well, the classic visualization, the one everyone kind of defaults to, is the tree structure. It's super intuitive, right? You instantly see the parent-child links, the branching structure, how mathematics comes under subjects. And importantly, this isn't just a visual aid for us humans. Tree structures map directly onto common ways. Computers store data, things like JSON or XML formats. So it's computationally very practical. The AI can work with it directly. It's like a natural fit for machines.
Right, it speaks the computer's language.
Yeah.
And the notes break down the tree terminology using that educational assessment system example, which is helpful. You've got the root at the top, the main concept, educational assessment system. Then parent nodes, like subjects, which have other nodes branching off them. Those nodes branching off are the child nodes, like mathematics under subjects. Nodes at the same level under the same parent are siblings, maybe quizzes and midterm exams under some assessment methods node. And depth just means how many levels down a node is from the root, starting at 0. It's a very clear logical map.
It is indeed very clear. Now, while tree diagrams are great visuals, we also need ways to write these down easily. The material highlights two common human-friendly ways. First, the simple outline. Just text-based, using indentation or bullet points, maybe numbers to show the levels. Super easy to create and edit. We all use outlines. And the second is the mind map. More visual, more radial. Starts with the main idea in the middle and branches out. Great for brainstorming, seeing the whole structure at a glance, maybe spotting connections you'd miss in a linear list. Both are just ways for us humans to sketch out that underlying hierarchical structure.
And this leads us to something really interesting mentioned in the notes, the bridge between how we read it and how AI reads it. And that bridge is Markdown.
Yes, Markdown. Its real power is being both human-readable and machine-readable. It's elegantly simple. You use plain text rules like a hash symbol, hashtag for a main heading, double hash, hashtag tag for a subheading, or dashes or asterisks for list items using indentation to show nesting. These aren't just formatting for our eyes, they are explicit structural cues for a machine. An LLM can parse this syntax. It doesn't just see words, it sees the hierarchy baked into the text. It understands the levels. It's a remarkably effective way to feed structured information directly to an AI.
Okay, so let's make that concrete. Using that educational assessment system, Markdown example from the notes, what's the difference in understanding?
For us, we look at it and instantly see, okay, subjects and grading system are the big chunks. And under subjects, there's mathematics and science. Our brains just process that visual structure. But the LLM, it's parsing the syntax. It sees hashtag educational assessment system, that's level 1, the root. It sees hashtag subjects level 2, a child of the root. It sees the indented mathematics under subjects, that's level 3, a child of subjects. So if you ask about algebra, which might be level 4 under mathematics, the AI knows through parsing that algebra is part of mathematics, which is part of subjects. It understands the context. And that structured understanding is absolutely fundamental for it to give relevant, accurate answers. It's not just guessing based on word proximity. It knows the relationship.
That clarity is crucial.
Yeah.
Okay, so we know why we need hierarchies and how we can represent them visually and textually, even for machines using Markdown. Now for the really cutting-edge part. How do we actually build these complex structures?
Yeah.
Especially using generative AI itself. The notes get into some specific techniques here.
Right. This is where things get really interesting operationally. The notes introduce a method called progressive outlining with generative AI, or PROGA. It's described as a systematic way to essentially mine a structured ontology, a hierarchy, from the LLM's own internal latent knowledge. The key idea is moving from general concepts down to specific details, step by step, in a controlled way. You're basically guiding the LLM to articulate its understanding in an organized fashion. And importantly, this approach helps manage the LLM's context window, how much information it can focus on at once. By drilling down into one branch at a time, you keep the context tight and relevant, preventing the AI from getting lost or sidetracked. It's like focused excavation.
Guiding the LLM. That sounds smart. So break it down for us. What are the actual steps in PROGA?
Okay, it starts with phase 1, primary category prompting. This gets you from depth 0, the root idea, to depth 1, the main branches. You give the LLM a broad concept and ask for the top-level categories. For instance, the prompt might be, outline the main daily tasks of a medical surgical nurse. The LLM gives you that first layer. Then phase 2, secondary category prompting, going from depth 1 to depth 2. You pick one of those main categories the LLM just gave you, say, patient assessment, and you feed it back as context in the next prompt. Something like, okay, you listed patient assessment. Now, please outline just the patient assessment task in more detail. What are its subcomponents? See, you're focusing the AI's attention on that one branch. And you keep going. Phase 3, tertiary category prompting, depth 2 to 3, and potentially further down. You take a subcomponent from the previous step, maybe initial assessment under patient assessment, and you prompt again. From your outline of patient assessment, expand on initial assessment. What specific steps does that involve? You iterate like this, level by level, building out the hierarchy with the AI's help, ensuring each new level connects logically to the one above.
Ah, I see. So this breadcrumb trail method, constantly feeding the previous output back as context. What does that do for the final result? The quality of the hierarchy?
It makes a massive difference to the quality. Huge. Providing that focused sequential context helps the LLM generate much more coherent, detailed, and accurate information at each deeper level. Think about it. If you just asked the LLM vaguely, tell me everything about nursing, you'd likely get a jumbled, maybe superficial, possibly inconsistent mess. But PROGA guides it. It forces structure. It transforms that vast, messy internal knowledge of the LLM into a well-organized, usable hierarchy. You're essentially collaborating with the AI to build an expert-level outline step by step. It also really helps reduce the chances of the AI hallucinating or going off on tangents because its focus is so constrained at each step.
That makes perfect sense. Constrained focus equals higher quality. So PROGA is step 1, the mining phase. What's the next piece described in the notes?
Right, PROGA is presented as the crucial first part of a larger two-step methodology called Omega. That stands for Ontology Model Emulation with Generative AI. Step 1 is ontology extraction. That's what PROGA does. It mines and builds that structured knowledge model, the blueprint, from the LLM, the hierarchy. Then step 2 is ontology-centered generation. This is where you use that extracted ontology. Once you have that validated hierarchy, the blueprint, you use it as a highly structured prompt or guide for the LLM to generate new content. Because the guide itself is so detailed and structured, the content the LLM produces, maybe a full report, a lesson plan, assessment questions, is much more likely to be high quality, coherent, and contextually accurate. It sticks to the plan. The really powerful idea behind Omega is this cycle. Use the AI to first emulate how an expert structures their knowledge via PROGA extraction, and then leverage that same structure to guide the AI in generating new, reliable, expert-quality content. It's moving beyond just generating text based on patterns towards generating structured knowledge products.
Wow, okay. We've covered a lot of ground here. It feels like we've gone from the problem, the chaotic sea of AI data, all the way to a potential solution. We talk about why structure, specifically ontology models, are so vital for AI understanding. We dug into hierarchical models, those key ASE and part-of relationships that seem so fundamental. We looked at how to represent them, trees, outlines, mind maps, and that clever use of Markdown. And just now, the cutting edge, using AI itself through PROGA and Omega to first extract and then use these knowledge structures really connects all the dots.
It really does. And it's important to stress, like you said, drawing from this work by Jae Choi and others in the field. This isn't just theoretical. This is about the practical development of AI that can actually reason better, understand context more deeply, and give us output we can trust. It's about moving beyond the limitations of just having massive amounts of unstructured data towards AI that has genuine, organized knowledge, closer to AI that truly understands.
So here's something to think about as we wrap up. Imagine how much more capable an AI could be if it didn't just have facts, but truly understood the relationships between them, that structure we've been talking about. Where could you, in your own work or maybe your studies, apply this idea, taking complex information and giving it that clear, logical, hierarchical structure to make real sense of it? Turning that data pile into a useful map, that's the power we're unlocking here.